Okay. Where does the glucose come from? They go back into your blood. Mouse. Glycogen in the liver. Perfect. 5 gold stars. Okay. Liver glycogen. Now liver right here. Okay. That glycogen stored in there. Whenever it dips, these hormones get released. That triggers breaking that glycogen down and then dump it into the bloodstream. In essence, to exactly match how much I need to bring me back up to here. Okay? Good. Okay. Are y'all with me so far? Right? You're with me so far. Good. Now, I will do this myself because y'all seem like you're not feeling it this morning. That's okay. Right? I start doing squats. Okay? Doing squats. What happens to my blood glucose while I'm squatting? Miles says down. Anybody else? What happens? Squatting, or if I'm just walking, strolling around, doing something, what happens to my blood glucose? That was the second. Increases, okay? Why would it increase?
So you'd be able to maintain energy.
Maintain the energy needed, okay? Okay. Anybody else? I just want to weigh in. You guys all agree it's go up? It actually doesn't go up, nor does it go down. Okay? There are things that are happening, but it basically stays constant. Okay? But when we exercise, pulls glucose into muscle cells. Okay? It pulls the glucose into muscle cells. We'll talk about why. The other thing that it does, that depending upon how you time things, could make it look like blood glucose is going up. Exercise increases liver glycogen breakdown. Okay? When you exercise, we drive glucose into cells, so we can use it as energy, right? But then in order to maintain blood glucose, we have to simultaneously start breaking liver glycogen down, dumping that liver glycogen into the bloodstream. Okay? It's also going to start breaking down fat, so we can dump fat into the muscle, so we'll stop using glucose altogether. It does several things. But this is, right, you're going to get both of these things, which functions to let us keep blood glucose as constant as we can. Okay? If blood glucose falls during exercise, you get central fatigue and you stop. Okay? You may not go into a coma, but if blood glucose falls, you stop exercise. So that's what we're trying to get. We're trying to understand and to maintain these processes. Okay? And we're going to use hormones and the acute change or release of certain hormones during exercise to help us regulate blood glucose levels and keep them constant. Okay. So as I start squatting, I am immediately sucking glucose out of my blood into my quads. That also stimulates almost, not exactly immediately, but very soon, right, the breakdown of glycogen in my liver as I squat. But that breakdown is going to lag a little bit because I have to squat and I have to start releasing hormones to tell the liver glycogen to break down. Okay? So we're going to talk about what hormones are involved in all of this. What is their change and their stimulus during exercise to change? And then what do they do? How do they all work together? But the overall goal is to essentially try to keep blood glucose levels constant. Okay. Does that make sense? Okay. So when you're walking 45 seconds and you're using aerobic metabolism, which I failed to explain to you adequately, you're pulling glucose in, but then you're also matching that by breaking it down from the liver. Sometimes you don't have to break it down from the liver, right? We eat a meal, Emma has some coffee, and we get a big spike, and if she went for a walk, then you can just walk and go lower it back down without getting the same hormone response if you've already got elevated blood glucose. Okay? And then really cool things happen where you do this and you exercise today, and your sensitivity to all of this changes for the couple of days afterwards. And that's why exercise can treat type 2 diabetes. Diet and exercise can almost exclusively treat early stage type 2 diabetes. Be physically active for the rest of your life, and you're almost guaranteed to not become a type 2 diabetic. Because we can regulate blood glucose, we can regulate insulin, we can regulate our sensitivity to all this stuff. Because the exercise is helpful. All right. Rant over. When we talk about hormones and exercise, this is my normal intro. People think about this, right? Say hormones, I say exercise, what you think of is testosterone, growth hormone, let's get jacked, right? And that's the thing that happens. But for most people, a way more important functional thing is all of this stuff with blood glucose that we've already talked about. And I will date myself with these slides because I'm too lazy to go back and change them. And there will be pictures and you'll be like, hey, that's from like 2004. Well, you all might not realize that because how old were y'all in 2000? Oh God. Some of y'all were not born in 2004, were you? Okay. I need a moment. I got old, right? My wonderful pictures of Sammy Sosa and Mark McGuire and Barry Bonds and all of these kinds of things. I mean, that's from the late 90s. And anyway, we usually think of exercise and hormones as muscle mass, testosterone, steroids, and we're like, wait, who is this? Yeah, it's okay. All right. When did I get old? Right? But you at least know who Lance Armstrong is. Y'all heard of Lance Armstrong? One of the world's worst human beings, maybe, right? I don't care how much money we gave, Live Strong and testosterone cancer and all of that. If you're a terrible person who lies and tries to basically get all the people that work for you and help you cheat in trouble while keeping yourself the same, to me, you're a pretty shitty person. But this, right? There's a hormone response during endurance exercise, right? Which, like the Iron Man, these kinds of things, right? That is not necessarily simply the anabolic hormone response. That is absolutely positively key to your ability to keep exercising for 3 weeks at a time for 6 hours a day. Okay. Any of you guys have Dr. Rebecca for Capstone? I know y'all have her like next. Ask her why on Monday or Sunday, whatever it was, why she rode the bike for 6 straight hours. She's just an animal. So on those things, she does all this. But this is what we're talking about is sort of endurance performance. Okay. We're going to talk about blood glucose. We're going to cover some of these other things a little bit later on in the rest of the class. We use hormones, okay, to also drive the cardiovascular changes during a lot of exercise, the pulmonary or respiratory changes during exercise to help us regulate fluid balance during and after exercise to help us modulate core body temperature during exercise, okay, and to help us from a metabolic standpoint, okay. So when things change during exercise, a lot of it is driven by hormonal changes that help us sense signals. And that should illustrate to you guys the importance of hormones, right? What a hormone really is, it's just a signal. It's like, hey, this is happening, tissue over here, do X, Y, Z. So we can make that happen more or less or something to that particular effect. Okay, and what you will see is that many hormones evoke similar or complementary functions across different systems. Okay. All right. There will be things that will change and will drive changes in substrate utilization, glucose, fat, moving those things around, but they will also have effects in the kidneys that help us with fluid balance, which helps us with sweating and controlling core body temperature and the like. So there's a lot of the stuff that's going to all be sort of worked in together. Okay. All right. So my next big picture kind of thing that's going to play into what we've already talked about. Our overall goal is maintain constant, flat blood glucose levels. Okay? That's the goal. When we exercise, energy demand goes up. Hopefully I've convinced you guys of all of that. Force goes up, ATP use goes up. We need more energy from somewhere. Okay? From somewhere. So demand goes up. One of the primary responses to that increased demand is to start pulling glucose out of blood so we can jam it through glycolysis to hopefully put pyruvate into the mitochondria, but if we need to make lactic acid. So blood glucose, there's a chance that when we exercise, blood glucose can fall. Right? And that can have poor negative consequences. So we're going to use our hormones, okay, to try to mobilize or break down stored glycogen to replace the lost blood glucose. But we're also going to use hormones to start mobilizing or breaking down stored free fatty acids in your adipose tissue. So we could put fat into the blood, and then we'll start using more fat for energy. And if we use fat, then we don't have to use blood glucose. Okay? It's a really important concept that I want to get across now, is that when exercise and blood glucose wants to fall because we're using more, we're going to do two things. We're going to match what comes out by breaking down liver glycogen. We're also going to overall stop trying to use so much glucose by switching and using fat. Okay? If we keep those two things in mind, then you should reasonably be able to predict what the hormones are going to change, how they're going to change, and what sort of a reaction we're going to get at their target tissue. Okay? Does that make sense? Right? Match what's getting taken out from a glucose standpoint, but also then just stop using it. If we don't use it, then it's not going to fall. Okay? Those are two really important things. Okay. So, mention this. I always love this sort of fake squishy picture of a brain. I gotta buy Ellis one of those. So she likes all these other different stuffies, but one of those. But in order to continue exercising, we need constant blood glucose so the brain stays happy. The brain will let you continue to generate force as long as it feels like there's a sufficient amount of glucose around to allow it. As soon as it begins to dip, because you've taken too much out, you can't match it with liver glycogen, right? You don't have enough fat mobilized to use it to preserve blood glucose. As soon as it begins to dip down for more than a couple of minutes during exercise, you're going to start feeling really shitty because the brain is like, shut it down. Shut it down when you stop. We're using too much blood glucose. Okay. I've asked this before. I don't think there's anybody in here. Nobody in here has ever done a marathon. One person. Remind me of your name. Kendall. When did you run a marathon last? Okay, so like less than a month ago. Okay, how'd you feel at about mile 20? Not great. Noticeably different.
Yeah, 20 to 26 was the hardest.
Were you just as motivated at mile 20 to run as you were like mile 2?
No.
No. Do you know why?
I'm assuming because of central fatigue.
Central fatigue. Now, you were able to keep going, right?
Mhm.
You could sort of will yourself to keep going, but you start to feel really bad because your muscle glycogen is all gone. So now when the muscle glycogen goes, you have to start using more carbs from blood glucose. So that's going to begin to start sort of dipping a little or have a chance to, and the brain just freaks out and says, we really should stop. We really should stop. And you can overcome that for a while, right? But that's the key. Did you drink any dairy while you were running?
I did gels too.
And you had some gels, okay? You consume all of that during the race, and about a half an hour to an hour later, it finally eventually makes it into your bloodstream and will try to raise your blood glucose levels back up to offset what we're taking out, so the brain says. Right? But you gotta master the timing really carefully, because when you run, the blood is no longer goes to your stomach or to your small intestines to do absorption to nearly the same extent. Okay. So we've talked about this, right? Hormones help with all of these processes. We've talked about what we're trying to match. Okay. So let's talk about a hormone. A hormone is a messenger. Okay. It's a messenger. It's a text message. All right. Or whatever it is y'all are DMing people with these days. It's WhatsApp message. I don't know. Y'all even do Snapchat anymore? I was that a thing? People Snapchat, I don't know. Okay. But it's a chemical messenger to make it a hormone that goes in the blood. Okay. Your pancreas releases insulin, insulin goes in the blood, and then it goes out and it circulates around and it goes to tissues that have insulin receptors. Okay. Hormones come from what we call endocrine organs. An endocrine organ is a organ that makes a hormone. Now, sort of a circular definition. But then we also have some things that are hormones, like epinephrine and norepinephrine, that come from endocrine organs, but they also come from nerves. And so sometimes epinephrine and norepinephrine are what we call the neurotransmitter. Other times they are hormone, and even though it's the same epi and norepi in that. Okay, so most of what we're going to talk about is all the endocrine organ function of all of these things. How do hormones work? You dump them into the blood, they float around in the blood, and then different tissues have specialized receptors for those hormones. So it's just floating around in the blood, it's floating around, it's floating around. Oh, look, here's my receptor. Bind to a receptor. Okay. Then, once it's bound to a receptor, it either gets pulled into that cell and it tells the cell to do something, right? Or it initiates a process, a second messenger system that sort of moves itself across the membrane. Okay? Not all cells have receptors for every hormone in your body. Right? Insulin's a great example. Muscle has lots of insulin receptors. Okay? I don't think your brain has insulin receptors. Okay? So certain cells have receptors for certain hormones. So we call those that tissue where those cells are sensitive to that hormone. Okay? And so that's how this process is going to work. And that's how you can say, you release epinephrine and norepinephrine. It does one thing in adipose tissue. It does a whole separate thing in the cardiovascular system. Okay? And so on. Okay? A lot of what hormones will do is they will tell the nucleus of a cell to make something. They will promote gene expression. Right? In addition to some other kind of function. You've seen this, we talked about this with, say, testosterone, or growth hormone, or IGF-1, right? It binds to a receptor, it goes in to the nucleus, it tells something to happen, signals through mTOR, it says make more active neurons. Okay? So the same stuff is gonna happen, but rather than synthesizing actin and myosin, we're gonna do stuff that helps us regulate blood glucose or regulate where fat is either in or out of adipose tissue and the like. Okay? There are two primary categories of hormones. And it's related to what the sort of the scaffolding molecule of that hormone is made out of. Okay? We call them steroid hormones and non-steroid hormones. Okay? So in this instance, I know that we generally talk about, when we say steroids or steroid hormones, you immediately think of sex hormones. You think of testosterone and estrogen and progesterone and those things. Okay? And that's right. But they are steroid hormones not because of their actions. They're steroid hormones because they're essentially made from fat, right? They are a steroid because of that scaffolding. They're derived from cholesterol. Steroid hormones, because they're made out of cholesterol, are not soluble in water. It's like pouring oil in water, okay? So to circulate them in your blood, which is mostly water, they have to bind to a carrier molecule of some kind. But it means that when they get to the membrane of your cell, they just pass right through. Okay? Your cell membranes are made of lipid. The hormone is a lipid-based hormone, so it just slides right through the membrane. And it goes and immediately acts on the nucleus. Now, the other kinds of hormones, we call them non-steroid. They're mostly made out of proteins. We call them peptide hormones. Peptide hormones generally tend to be water soluble, so they go in your blood, they just float around, they don't need to bind them. Okay. But when they get to a cell, they have to bind to a receptor on the surface because they're protein, they're not lipid, they cannot pass across the cell membrane. Okay. So not only do these hormones have different actions based upon what they are, the type of hormone is going to govern where the receptor for that hormone is going to be located. Okay, so we will talk about several steroid hormones, testosterone, estrogen. We've talked about them to an extent. They don't play a huge role in regulating blood glucose. Okay? Cortisol does. Cortisol is a steroid hormone. And we'll talk about peptide hormones, insulin, glucagon, epinephrine, norepinephrine. Okay? So it's going to be an important thing for you guys to know. For the list of hormones that I'm going to give you, are they steroid or are they peptide? Okay. So we'll try to get our way through all of that. Here's a cartoon. You have steroid hormone, we're out of the blood out here. Here's the hormone bound to its carrier molecule, often a protein, something like that. Gets to the cell membrane, it passes right through the cell membrane, and it either binds onto a receptor in the cytoplasm or it binds onto a receptor in the nucleus, and then it initiates its actions. Okay? Here is a peptide hormone. At the very top, that's the blood. The hormone not bound to a carrier, floating around into the blood, binds to its receptor on the membrane, then that usually activates this second messenger cascade. This one here is coupled to a G protein. We're not going to talk about G proteins. You're going to have to learn about all the G proteins. They typically then signal through something called adenylate cyclase, and you make cyclic AMP and blah, 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 blah. And you activate these kinases and you stick phosphates on the things. And eventually you get down here to the thing. Okay. I assume you guys talked about all of this in human phys, probably, yes, in intro to bio and all of those things. I love a good signaling pathway, but we don't know any of those things here. Okay. There's different kinds of G proteins that signal through different sort of mechanisms. You don't know any of that. Okay. I just want you to know it's a peptide hormone, so it's a surface receptor. Here are the kind of primary endocrine organs that we're gonna discuss hormones that are gonna come from these organs. Okay. The hypothalamus, so the brain, is an endocrine organ. Okay. You've got the hypothalamus, regulates everything in your body. You've got the pituitary, Okay, that generally responds to things coming from the hypothalamus. You have your thyroid, which is right here, okay, plays a huge role in controlling metabolism, right? We then have the adrenal glands, which are going to sit on top of your kidneys, okay? There's the adrenal medulla and the adrenal cortex. The medulla tends to make epi and norepi, right? The cortex makes cortisol. You've got the pancreas right down here. Insulin and glucagon come from the pancreas. Huge role in regulating blood glucose from the pancreas. Okay. We then have the kidneys themselves. Most of what the kidneys make is going to be related to fluid balance, okay, and red blood cell content. And then we have what's sort of collectively called the gonads, so those would be ovaries or testes, depending upon if you are sort of male or female at birth in those particular ways. Okay, so we're not gonna spend a lot of time talking about testosterone and estrogen and progesterone and those other sorts of things there, but those are endocrine. Okay. When we go through each of our hormones, I also want you to know where that hormone comes from. What is its endocrine order? Okay. So you need to know insulin comes from the pancreas. It's a peptide hormone comes from the pancreas. Right. Then we're going to figure out what does it actually do? What's its action? Okay. Okay. So let's talk about insulin. Okay. Let's talk about insulin. Insulin is one of, if not the, Dr. Pinky would probably tell me it was the, right? This is the sort of primary hormone that we use to regulate blood glucose levels. And its primary use is to take blood glucose levels and lower them down. Okay? Insulin comes from the beta cells in the pancreas. It's important that you know the beta cells. Okay? It's important that you know the beta cells. Don't have to know that it comes from the beta cells and the islets of Langerhans, but beta cells. It's a peptide hormone. The thing that drives the release of insulin is elevated blood glucose. Okay. I've been talking for a while, right? Emma has probably released some insulin by this point in class. Okay. She's drinking a coffee. I was talking about this a half an hour ago. She's probably had an increase in blood glucose since then. Okay. As blood glucose ticks upwards, the pancreas senses that increase and it releases insulin. Insulin is a peptide hormone, so it floats around, it gets in your blood, and then it binds to receptors on the surface of tissues that are sensitive to insulin, have receptors for insulin. Okay. The big thing, the big tissue that needs this is going to be the liver and muscle. Okay. When insulin binds to its receptor on skeletal muscle, okay, it initiates a process inside of your muscle cell whereby it moves receptors for glucose from inside the cell out to the cell surface. So that when glucose floats by that cell, it may bump into that receptor and then it will grab and pull that glucose into the cell. That lowers your blood glucose. The insulin receptor, and I want you to know this, the insulin receptor that glucose initiates moving to the membrane is called GLUT4. Okay. Yes, there is a GLUT1 and a GLUT2 and a GLUT3, I think up to like a GLUT8 or 9. But the one that insulin promotes is GLUT4. Okay. All of you have sitting there right now stored GLUT4 receptors inside your muscle. They're all in there. They're just waiting for insulin to float by and tell the cell to move them out to the membrane so it can grab glucose. When blood glucose levels begin to go back down to normal, insulin levels drop, There's no more insulin on these receptors, and after a certain amount of time, you take those GLUT4 receptors and you just pull them back out of the membrane, and they come back in here and they get repackaged up, and they wait for the next insulin signal. Okay. That's how insulin gets blood glucose falling. Okay. Now you guys remember, and I said when I start doing squats, right? I'm going to start pulling glucose into my muscle cells because I need it for energy, right? Okay. Exercise or muscle contractions do the exact same thing that insulin does. Call this the insulin-like effect of exercise. You contract a muscle, and the contraction, there's no insulin involved. The contraction signals to move GLUT4 from inside the cell to the cell membrane to start pulling glucose in. Because it just knows we're using more energy. It would be good if we had some glucose in. Okay? It stimulates the same pathway. We don't know how. We sort of know why, but we don't know how. They've been trying to figure this out for about 60 years. We will one day understand all of the individual signals, and that person will win a Nobel Prize because you will have cured diabetes. Okay? So we can make a drug that targets those same kinds of things. That's what exercise is. Okay? There's going to be some weird things that happen with insulin during exercise because the contractions function in the same way. Okay? I don't remember, I should ask. Do we have anyone that's type 1 diabetic in class? Do we have any type 1 diabetics? Any of you know it's type 1? Few of you? Okay. Do they have insulin pumps? Most people, a lot of people do now. Okay. The pumps make life a little bit easier. But in the olden days, you give yourself a shot, right? For any of you that ever want to know somebody's a type 1 diabetic, single most dangerous thing they can do is to go exercise. Okay? Because, and I'm being a little hyperbolic, but it's exercise is incredibly dangerous to type 1 diabetic. If their insulin levels are not properly regulated, they can exercise, which will pull glucose out of their blood. And if let's just say they're going to exercise and they just took an insulin shot and their insulin pump says, here's some insulin. The insulin then also stimulates this pathway and tries to pull glucose out of their blood. So it can be extremely dangerous when you get the combination of both of those things at the same time. You get a dramatic fall in blood glucose because you get the insulin effect plus the insulin-like effect from exercise. So that's why we basically tell type 1 diabetics, if you're ever going to go exercise, eat a candy bar. Drink some Gatorade before. We want to make sure that we can basically get you in a place where your blood glucose is sufficiently high for your exercise, because there could be both of those things happening. All right. That's here. That's what goes on. Okay. So insulin is the weird. I guess the happens is I'm exercising, I want to control blood glucose. You might think insulin drives glucose into cells. That's what we want during exercise. So maybe insulin should go up. What actually happens to insulin during exercise is insulin levels plummet. They plummet. During exercise, we do not release insulin. Okay? And that may seem a little backwards, but it's to protect you from having too dramatic a fall in blood glucose. Muscle contractions are pulling in a good amount of glucose, so we don't need help from this. Okay? I'll give you guys a little hint for what we're going to talk about on Friday. Every other hormone we're going to talk about with exercise goes up. Insulin does not. Insulin goes back. All directions go. All right, we'll leave it here. We'll finish this off on Friday. We'll do a big class assignment. on Friday, for those of you guys that are here. For those of you who aren't, have a lovely spring break, I guess. We'll see you on the other side. Okay, bye, guys.
Hello.